Hello everyone, and welcome to Biopedia. As we touched on back in episode 24, quite a number of alleles come in either a dominant or a recessive form. This then results in dominant or recessive phenotypes, with individuals being either homozygous dominant, having two copies of the dominant allele, heterozygous, one of each allele, or homozygous recessive, two copies of the recessive allele in their genotype, which then translates to this phenotype. But how does the frequency of the dominant versus the recessive allele in a population translate into the frequency of genotypes or phenotypes? Well, that's where the Hardy-Weinberg equation comes in. This equation is named for the two men who came up with it independently in the early 20th century, G.H. Hardy and Wilhelm Weinberg. The equation states that if the frequency of the dominant allele in a population is given by P, and the frequency of a recessive allele is given by Q, then the frequency of phenotypes together should be P squared plus 2PQ plus Q squared, with each term referring to the homozygous dominant, heterozygous, and homozygous recessive genotypes respectively. All of the terms in this equation should then be equal to 1, referring to 100% of the population. Similarly, when referring to individual alleles, the equation is P plus Q equals 1. Now, hang on, I hear you all shouting. What does this mean? Well, the best way for me to explain is with an example. Say that there's a gene where the dominant version results in blue hair and the recessive version in green hair in a population of 100 people. This would give you 200 alleles in total in the population, as each person will have two copies of the gene, regardless of which alleles they have. Now suppose that, once you've counted out all the alleles, there were 100 dominant and 100 recessive alleles in these 200 total. This would mean that the frequency of the blue allele, or P, is 0.5, because there are 100 out of the 200 total alleles. Likewise, for the frequency of our green recessive allele, referred to as Q again, it's also 0.5. Because all alleles have to be either dominant or recessive, we can assume that P plus Q together is equal to 1. So why is the first equation that I mentioned more complex? Well, each individual has two copies of the gene, which needs to be taken into account when discussing genotypes rather than simply allele frequencies. Each of these genes needs to be treated independently of the other. As such, you take the equation that we just covered, P plus Q equals 1, and square it. After multiplying out the brackets, this yields the equation we first discussed, P squared plus 2PQ plus Q squared equals 1, which tells you the total genotype frequency in a population rather than simply the allele frequency. So, referring again to our example from above, the frequency of the dominant genotype would be P squared, or 0.5 squared, which gives you 0.25 or 25% of the population. Similarly, carrying this on for the other two genotypes, you would end up with 50% for heterozygotes and 25% again for the frequency of the homozygous recessive genotype. In theory, once you work out the parent population's genotype frequencies, these same frequencies should carry over to the next generation unchanged. If this happens, the population in question is said to be in Hardy-Weinberg Equilibrium. However, in order to do this, the population itself has to meet some strict criteria. Now, a few years ago, I found a really interesting video by TED-Ed, which I've referenced in the show notes, which taught me a way to remember the 5 mechanisms behind evolution. Now, I'm not going to go into that method here, but the point is that there are generally 5 mechanisms behind a population evolving. These are genetic drift, sexual selection, mutation, gene flow, and natural selection. Any one or more of these 5 mechanisms will change the allele frequency in a population from one generation to another and cause an evolutionary change, as incidentally we discussed all the way back in episode 19. So, in order to be in Hardy-Weinberg equilibrium, we basically have to assume that none of these 5 mechanisms apply. So, in the same order, first of all, we assume that a population is infinite in extent to avoid the effects of genetic drift. After all, genetic drift is essentially a sampling error but for biology, and its effects diminish as a population's size increases. To mitigate the other four factors, it is further assumed that mating is random, that there are no new mutations, that there is no gene flow, and that natural selection is not occurring. So, why is this relevant? Well, these very restrictive assumptions essentially means that the Hardy-Weinberg Equilibrium can serve as a null model for evolution. What this means is that we can test whether these frequencies are significantly different between generations using a chi-squared test on the observed versus the expected genotype frequencies. If we don't see allele frequencies remaining constant between generations, at least one of these 5 processes mentioned above is occurring, and evolution is therefore taking place. Now, of course, it is alternatively possible that there is a sampling error, but assuming that this is not a case, evolution can therefore be observed in action. One further note on this genotyping error. After studying a dataset of 3,204 genomes, a 2017 paper noted that a rise in heterozygote frequency was generally associated with this genotyping error, but a drop in heterozygosity was not. An example of a genotyping error was given as an allelic dropout, or an allele not being picked up. The authors state that this is less likely to be noticed at a homozygous locus versus a heterozygous one, given that both a heterozygous locus and a homozygous dropout locus would both appear as one band in the results, and thus heterozygotes would have an increased chance of being detected. So, that's the Hardy-Weinberg equation. As always, thank you all for listening. Feel free to get in touch at the show's email address for any questions, comments, or topic suggestions for future episodes. Until next time, have a great week, everyone.